All right, so now we're getting a little bit more AP in nature, all right? The other ones were all kind of introductory, basic ideas, possibly something you'd see on a multiple choice, but now we're getting into a little bit deeper, trying to understand a little bit more, put those ideas to use. Here we go. We've got this circuit. It's got a couple of switches in there. It does have a capacitor. It's got a battery. It's got a couple of resistors. All right, let's jump right into it. So the first thing it says is that switches 1 and 2 are both going to be closed, which means that my current is going to flow through my circuit just like this. Nothing is going to go over to that capacitor yet because S3 is still open, but I am going to have that there. So the question is calculate the current through R1 and R2. Well, in order to do that, I'm going to need to know the total resistance. Because they're in series, then I know that the resistance total is going to be 10 ohms. I just add them together because they're in series. You can check that formula in your formula packet if you want to. Now that I know the total resistance, I can use the formula I equals delta V over R, which then will allow me to find the current, because I know that the total potential is 30 volts and the resistance is 10 ohms, and so I get 3 amperes. There we go. Now, because they're in series, the same current has to go through all of them, right? It's not going to change. Okay. Now, in part B, it says switch 2 is opened. So now switch 1 is closed, and it says switch 3 is closed. So now, instead of the current going through the middle, the current is now going to go all the way around the outside. So it's going to go around like this. All right, because 2 is open, 3 is closed. Calculate the current through R1 and R2 and the charge on the capacitor immediately after the switch is closed. Okay, well, immediately after the switch is closed, we already know that the charge on the capacitor is 0 coulombs. We know that's the case because the current hasn't started flowing yet. As soon as the switch is closed, there's no charge there. We treat it as if it was no potential difference, no charge, just a wire. Now, the next question is, well, find the current through R1 and R2. Well, R2 doesn't have any current. Now, that should make sense as well because there's no current flowing there, right? If that switch S2 is open, no current's going to flow through that section of the wire. All the current is marked by the blue there is going around the outside. Now, at this point, I can find the current going through R1. Now, again, I'm going to use that I equals delta V over R. And I know that the delta V is going to be 30. And the resistance is 6, giving me 5 amperes. Now, this should make sense. Remember when we initially connect that capacitance there, we essentially treat it as if it were a wire. So therefore, all of the potential must be lost in that resistor. Before, some of it was lost in the R2, which meant more total resistance, so less current. But now there's less resistance, so there should end up being more current going through that resistor. We've now answered all the questions for letter B. Now, letter C says, calculate the currents through R1 and R2 and the charge on capacitor C a long time after switch 3 is closed. So still same situation, 2 is open, 1 and 3 are closed. Now what that means, still no current going through R2, right? That still has to be 0. Now at this point, the capacitor should be fully charged after a long time. Now, the first result of that, if C is fully charged, that means that C is going to have a potential difference of 30 volts. Now, if it has a potential difference of 30 volts, then that means that the resistor number 1, won't have any potential at all. And if there's no potential drop there, it's because there's no current. That should make sense because if this potential is less than 30, then current will flow. If current is flowing, potential is going to be lost in resistor 1. And so as time progresses, the current will get slower and slower and slower, so there will be no potential lost eventually in that resistor number 1. So again, we'll say the current through resistor number 1 is also 0 amps. Now, this asks now for the charge on capacitor C. Now, in order to do that, we're going to use our potential equals Q over C. The potential is 30 volts. The charge is what we're looking for. And the capacitance there is 25 microfarads. And so we just multiply the 30 times the 20, 5, and we get 750 microcoulombs for our charge. There we go, completed letter C. Now letter D is a little bit different. It says sketch the current versus time graph. I think this should be for resistor 1 over a long period of time after S3 was closed. So we sketch a little graph there. We got current versus time. This is for R1. We know that initially it started with a whole bunch of current, right? We solved in part B that it had 5 amps of current. And then after a long time, it got down to 0 amps of current. Now, if you solved for values earlier in the question, you should include those in your graph. If you have time, you should find initial and final points. You should find a couple of points that you can put into your graph there. All right. If you haven't solved for it before and you don't have time, then a general quick sketch is fine. Don't waste time. But first off, if you have those numbers, you better put them in the graph. Second off, if you have the extra time, it's always worth just taking that extra time to put a couple of values onto your graph when possible, at least the initial and final. Okay, now as we put this in, the question is, well, should it be straight or should it not be straight? Well, hopefully, as you think about it, initially you have a very large driving force, right? Which means lots and lots of current is going to flow. Now, if lots of current flows, it's going to change the potential quickly. Now, as the potential is changing quickly, we know that V equals IR, so therefore the current should change quickly. But as time progresses, the capacitor is filling up with charge, and so the current is flowing less and less. The change in the potential will be less than it was before. It will change at a much slower rate because the current is flowing at a much slower rate. And so the capacitor is filling up with charge at a much slower rate. And so therefore, it should change rapidly at the beginning, and then as time progresses, it should flatten out. Now, those that are math geniuses, or not geniuses, but that are really good at math may recognize, yeah, this is kind of that exponential feel of a graph, right? It changes rapidly at the beginning, and then it changes and slows down over time. Really, we would like for there to be some type of asymptote there. But the reality is that there is a finite size of an electron, and you can't, eventually you get to the point where either the last electron goes, or the last electron doesn't go. And at some point, the last electron is going to fill up that capacitor. We are going to get down to 0 amps at some point, right? And so yes, it's exponential, but the reality is there won't be an asymptote. It will eventually touch that x-axis. All right? Now, we're on to letter E. A long time after switch 3 is closed, the switch 1 is opened, and switch 2 is closed. Whew, this is getting crazy. So now switch 1 is going to open, which means no current is going to go there. That means the battery isn't going to be important anymore because the battery is no longer in our circuit. But remember, our capacitor is charged, so we've got a positive here and a negative here. And so the current now, 2 is going to be closed. So now we're going to follow through that green loop there. All right? So we now have 3 closed, 2 is closed, 1 is open. So we now want to calculate the currents through R1 and R2 immediately after the switch is closed. All right, well, R1, 0. Right? Because R1 is now in that section that the switch is open. There shouldn't be any current flowing there. All right? Now, R2 is in the section with the capacitor, and the capacitor initially has a potential difference of 30 volts. And so we can calculate I equals delta V over R, because there will be 30 volts there initially. The resistance of that resistor is 4. And so when I do the 30 divided by 4, I should get a value of 7.5 amperes. All right, so we got 7.5 amperes there. For our current, that is for the resistor 2. And that's the answer to letter E. We're ready to move on to F. It says calculate the currents through R1 and R2 and the charge on C a long time after switch S2 is closed. All right, well, a long time after S2 is closed, the current is going to flow through this green loop, and all of the electrons that are on the negative side are going to end up on the positive side of the capacitor, so the charge on C should end up being 0. Now, if the charge on C is 0, the battery isn't connected anymore because that S1 is still open. That means that I'm not going to have any current through R1 or R2. We're at a point now where all the current's been used up. We've unplugged the device. It's no longer connected to a power source. Therefore, it is going to turn off. All right. So, in this situation, R2 could be viewed as kind of that power light, right? That power light that is being powered by the capacitor until the point in time that the capacitor's energy has all been used up and now down to 0. All right. The last bit here, it says, sketch the current versus time graph for R2 over a long period of time after S2 is closed. All right, so let's draw a graph here. So we've got the current in R2 and the time. Now, in this situation, the current initially was high, right? We found that it was 7.5 amps. Again, I've got that information, so I'm going to include it here. And after a long time, it will be down to 0 amps right here. At a long time infinity, same principle here. When I have a large potential difference across the C, then there's going to be a lot of charge flowing. But more charge flowing means more charge leaving, which means the potential is going to change very rapidly, and so therefore, so is the current. Okay, as that passes, then eventually it's going to slow down, something like this. We should again get some type of more or less exponential graph. It doesn't have to be perfect. They want to see, number one, that the current is decreasing over time, and they want to see, number two, that you recognize that it's not going to be linear. It is going to be kind of this exponential style graph. Okay? That's it. We've answered all the questions on number 15. This is a lot of good conceptual questions. Make sure you understand what happens when a switch closes, what happens when a switch opens. Is there any current flowing through that branch of the wire at all? If the switch is open in that branch, no current should be going there. All right. Secondly, what is connected to the capacitor? If it's in the same branch as the capacitor, then whatever's happening to the capacitor has to be happening to that. As the capacitor fills up, then there won't be any current flowing anymore. All right. So that's great for this example. Let's go ahead and watch another.